So in this video, we will be learning all about optimizers in PyTorch, right? But in order to understand what are optimizers, first let's look at this neural network diagram we have here on the screen, right? So we have our input layer, we have our hidden layer, two hidden layers, and then we have our output layer. So what the output layer is doing here is basically once we give our inputs to the neural network, we get our output, which is a predicted value through the output layer. So all the calculations that are done by the hidden layers. As you can see here, hidden layer 1 and hidden layer 2, right? So let's go ahead and look at how the calculations are performed. So say we have two inputs passed in our input layer, input 1 and input 2. It could be anything. Maybe we can say input 1 is our age and input 2 is our salary, and this is our output. Right? So in order to get our output, which is our CJPA, first what we're going to do is we're going to pass our age, say 19, and salary 0 as our input 1 and input 2. Then what we have is our weight functions, right? So these weights could have any value, but preferably they are kept near 0. You can say 0.1, 0.2 and so on, like they're kept really small. So these weights are in general very small in order to have optimum results, right? Then we have our hidden layer, which is basically an activation function applied. So we can say this is a linear regression type learning algorithm. So preferably our activation function over here is going to be a linear activation. And then finally, whatever output is provided by the hidden layer is further multiplied with our weights, and then finally the output is calculated, right? But whatever output is going to be provided, whatever our predicted value is, it might sometimes be really close. Suppose we might get a 6.5, or maybe we could get 7 over here, or maybe it could range, right? Our predicted value depends all upon our calculations over here. So whatever our predicted value here is, let's call it y hat, and this value, our actual value, let's call it y. So the difference between y and y hat is basically what is known as our loss. So in order to have a really good model, or you can say a high accuracy model, what we want is we want this loss to be really less. We want this loss to be as minimum as possible. So how can we achieve that? That is done with the help of optimizers. This is where optimizers come in the picture, right? So what these optimizers do, they basically backtrack and somehow update these weights in such a manner so that our output finally, when we calculate it, is as close, or the loss is as minimum as possible, right? So after applying optimizers, say we would get a value 6.5, and you could say without applying optimizers we could get our predicted value as somewhere around 7, right? Which is not very far, but again, it is not a good it would not give a good loss, right? So let's go ahead and understand our optimizers. First one would be gradient descent. So this is what we covered in our backpropagation video. You can go ahead and check it out. So what happens in gradient descent basically is, so you can say gradient descent has, let's say we have a basic equation mx plus c, right? This is our y hat. So our loss is basically going to be y minus y hat, which is nothing but y minus mx minus c, right? So we can say gradient descent is an iterative approach to finding the optimized value for our weights and biases, right? So let's say we have loss versus weight, and this is our graph, right? So in order to have the minimum loss, we're going to traverse this graph until we reach a point which represents our, you can say, global minima, right? So say initially we have our weights over here, or you could say somewhere over here. So we have to traverse this graph in such a way that we travel towards the global minima. So this process is done by calculating the slope, right? So you can calculate this. So basically you can calculate the slope by using the basic equation, that is dy by dx, or you can say delta y by delta x. That gives us the slope. Y is nothing but loss and x is nothing but our weight, right? So this point we would have our slope somewhere over here, and at this point we would have it somewhere over here, right? So this over here is our positive slope, and this over here is our negative slope, right? So whenever we have our slope as positive, we have to go in a direction having, okay, so this our weight here is basically our intercept, let's call it c, right? So whenever we have a positive slope, we have to go in a direction that reduces our intercept, that reduces our weight, right? So we go in a direction like this. Over here, when we have a negative slope, we go in a direction that is increasing our weight. So this is how we reach the global minimum. And the process of reaching the global minima is called convergence. So this is a term. So this is a term that you will be coming across a lot. Reaching the convergence is basically the point where you find your global minimum, right? So how do you know when you have reached the convergence? It is basically when you have your C new minus C old somewhere around 0.001, right? Or you can say 0.001. So this is how you know you've reached convergence. Now what is C new, what is C old? Let's look at this formula. So basically the formula for gradient descent can be calculated by C old minus the slope. Now our slope is basically this, right? So we can say, minus delta loss by delta weight. Our weight over here is C, right? Now in order to repeat, but this formula here is a little incomplete. Let me tell you why. If we directly go ahead and use this formula to calculate our new weights, to update our weights, the problem here is going to be, it is going to take regular jumps, right? And by taking regular jumps, there is this issue where it might skip the global minimum. So there could arise a condition where it goes in a state where it is constantly repeating and never reaching the global minimum. So in order to avoid that, we introduce something known as learning rate. Which is nothing but our new, right? So this learning rate is multiplied by the slope. So this can also be written as delta W, right? Because this is our... So our learning rate is basically a tuning parameter which determines the step size at each iteration while moving towards a minimum loss, right? So if you see this graph, instead of taking regular steps, our learning rate is going to define how we move towards the global minimum, right? So usually an ideal learning rate value is 0.01, right? So this is what the general learning rate value is by default. So let's take an example. Let's say we have an equation, say y equal to x square plus 2, right? And in order to find the slope at say point 10, x equal to 10, right? So let's find the slope, 2x plus 0, so it is just 2x. So 2, and then we put the value of x, which is 10, so it becomes 20. So this is our, so you can say this is our gradient or slope, right? So let's apply it in the equation. Our equation is, let's call it W new, since we are updating our weight, W old minus learning rate into delta loss by delta W, right? So our W old is, let's consider it as minus 10. Let's say our learning rate is 0.01, and this we just calculated out to be 20, right? So it is minus 10 minus 2, so it turns out to be minus 12, right? So this is how you calculate the gradients. Now let's go ahead and dive deeper into the types of gradient descents, right? The first one is batch or vanilla gradient descent. So this is the most basic gradient descent available in PyTorch, right? So what happens here is the entire data set. Suppose we have a data set containing 50 rows, or you can say 50 data points, right? So these entire 50 data points will be passed at once in our function. So we have here is epochs. The number of epochs are defined over here. Epochs is basically the number of times our data set is passed in the algorithm, right? So we have 10 epochs, which are 50 data points are going to be passed in at once. So in batch descent, the total number of times our weights are updated is equal to the number of epochs. So over here 10 times our weight will be updated. Here we have delta of loss upon delta of W, right? So this is what our pseudocode will look like. For I in range, which is 10 epoch, we calculate our y hat, which is a predicted value, using np dot. Np is nothing but numpy. We use the dot operation to multiply our input data and our weight, and then we add our bias, right? We calculate our loss using the formula y minus y hat to the power 2, which is nothing but y minus y hat square, and then we update our weight using the gradient descent function, right? So this entire process is done 10 times, and then finally we reach to a loss which is minimum. In case we don't reach, in case our loss is still a little higher than what we wanted, we would simply go ahead and increase the number of epochs. Say from 10 we jump to 100. So at the 100th epoch, we check our weights, we check our loss, and we see if this is what our optimum loss should look like. If not, we go ahead and further increase our epochs, right? So this process can be done in number of times. So let's go ahead and look at the advantages of batch or vanilla gradient descent. So it has the fastest runtime. Now this fastest word here is used with respect to the other two gradient descent, which is stochastic and mini batch. So compared to these two other optimizers, we have concluded that this one has the fastest runtime, and it also has lesser noise compared to these two optimizers, right? We'll go ahead and look at stochastic and mini batch. So what stochastic gradient descent here is, it's basically known as SGD optimizer. So what SGD does here, it basically takes a single random sample at a time and then calculates the weight and updates the biases for each random sample, right? So let's understand the pseudocode first. So we have defined the epochs. We have run a loop for 10 epochs for now. And then what we're doing here is we're choosing a random X value. So say we have a data set, right? So from all these 50 points, say we have 50 points again. So from these 50 points, we randomly choose any one point. Okay? So, and then what we do here is we run another for loop. And what shape does is shape returns the number of rows and columns, right? So what we're doing here is we're running a loop for, we have 50 rows, so we're running a loop for 50. We're going to run the loop for 50 times, just for this example. And then we're going to calculate the y hat, and then we're going to calculate the y hat using the same np dot function, passing our x value and our weights, and then updating the loss and updating our weights as well. So this is going to happen another 50 times. We choose a random x value, we run the loop. This shuffling should happen over here, right? Once we run the loop for our 50 rows, we randomly choose one of the rows, you can say one of the x value, and then we perform the calculation. So over here what we have is we also have y as a list of 50 actual values, and then we create another list y hat of 50 predicted values, and then we calculate the loss using y and y hat, and then we update our weights. So the total number of times our weight is updated is basically number of epochs into our number of data points. So here we have 10 epochs and 50 data points, so 500 times our weight is going to be updated. So you can see why this has a lower runtime compared to our batch gradient descent or vanilla gradient descent. But an advantage over here is it has a faster convergence. Fastest again here is compared to batch gradient descent and mini batch gradient descent, right? So it has the fastest convergence and it is more efficient for larger data sets. Let's look at the loss plot before going further. So a loss plot would look something like this, right? So basically what is happening here is till it reaches the lower points, like you can say this is our graph. So till here when it's traveling, once it's reached the valley, the lower valley, once it's reaching closer to the global minimum, it's fine, right? You can see, but once it's reached here, it gets really spiky. You can see here the graph gets really spiky. So this is something that we do not want in our repeat. So this is something that is not preferred in optimizers. So this is where mini batch gradient descent comes in the picture, right? So this is basically best of batch gradient descent and stochastic gradient descent. So what we're doing here is we have a data set of 50 data points, right? This is our total data set size. So what we're going to do is we're going to divide it in say 5 batches. So each batch is going to have 10 data points, right? Each batch. So our number of batches over here is going to be 5. Our epochs is 10. So for each batch means for every 10 data points, we calculate the y hat, we calculate the loss, and then we update the weights and biases. So you can say the total number of times our weights and biases are updated is basically epochs into batch size, which is nothing but 10 into 5, 50. So the loss plot for mini batch gradient descent would be similar to SGD, but it would be lesser spiky, right? So this is why it is better than SGD. Let's look at some of the advantages. So the runtime and convergence lies between batch and stochastic. So you can say the runtime will look something like this. We have our batch, mini is going to be in between, mini batch, and then we're going to have SGD. So SGD has the lowest runtime. Convergence, again, mini batch is going to be in between, having an average of SGD and batch. Batch is going to have the lowest convergence. So this is why we say mini batch is a better version of both batch and stochastic. So, and it is also comparatively has a more stable convergence, right? You can see here. So now, since we already have 3 gradient descents and we have a lot of other optimizers as well, let's understand why we needed the other optimizers in the first place. So there are some challenges with gradient descent. The first one is saddle point in non-convex. So first, to understand saddle point, let's understand non-convex. Convex and non-convex, right? So as you can see, these 2 graphs here, these are 2 3D graphs. You can say this is our loss. Let's say this over here is our weight 1, and let's say this one is our weight 2, right? So we're having 3 parameters over here, which according to which we have plotted a 3D graph. So you can say this is a convex loss function, right? Because as you can see, we have only one global minima over here. There is no other local minima, right? This entire graph has only one point which is going to the minimum value. But look at this non-convex graph here. It has a lot of local minimas. You can say this valley over here, this drop could be a global minimum. But in case we start here, we would travel somewhere over here, and we would reach a local minimum. So whenever we use gradient descent, there is this problem of local minimum in non-convex problems, right? Once we reach this point, it would be very difficult for a gradient descent optimizer to move out of this local minima and then travel to the global minimum. Or you can say that here is another local minimum. So depending on our starting point, if our starting point is here, we would easily reach the global minima. But for this to happen, the chances are very less, because our starting point may not always be over here, right? It could start over here, it could start over here. So according to that, we need to choose our algorithm, right? So now that we've understood convex and non-convex, let's understand saddle point. So saddle point is basically, say we have a graph that looks something like this, right? So saddle point is basically something like this, where we have a graph which is somewhat straight, or you can say there is no curve over here as such, and you can consider this part, right? So these are our saddle points. It is these points where our learning basically stops. Since the slope of our cost function, this is our cost function, right? This is our loss, and this is our weight on our x-axis. So when we have a graph like this, we can say our learning, you can see over here, when we find the slope, which is basically dl upon dw, it is going to be approximately 0, right? So in cases like this, we have our saddle points, and this is where our learning stops. So you could say if our starting point is here, we would travel all the way till here, and our algorithm, which is our gradient descent, would conclude this to be our global minimum, or you can say the lowest loss could reach, right? Because once we start reaching over here, our learning would stop. So this is a problem that arises in gradient descent. Another thing is learning rate. So since you know, our formula to update the weights is something like this, right? W new equal to W old, which is our previous weight, and then we subtract the learning rate multiplied by our gradient of loss, right? So you can see that our entire process depends on our learning rate. So to find the exact optimum learning rate is a problem sometimes. So this is where, suppose we have our loss function graph like this. We start over here, we want to reach over here our global minimum. Say we start going initially like this, and then as our learning rate decreases, so this would what our learning rate would look like, right? So in order to find the optimum learning rate, we need to again have a lot of calculations. So this is again a problem in gradient descent. Another challenge in gradient descent is we cannot have different learning rates for each parameter. Now if you look at this graph, we have our global minima somewhere over here, right? But for this graph, we need to have different parameters. We need to move in this direction, and then we need to stop moving in this direction and start moving in this direction somewhere. Or you can say we need to move in this direction to reach our global minimum. But in order to do so, we cannot have the same learning rates for each parameter. We can say this is a W1 and this over here is W2. If we move in W2 and W1 in the same at the same pace, we might not reach at the global minimum, right? So what we need is we need to train our weights in such a way that one weight might have a different learning rate and the other weight might have a different learning rate, so that we reach the global minima optimally, right? The other one is local minima, which we've already discussed. So this is why we have other optimizers, and the first one is gradient descent with momentum, stochastic gradient descent with momentum. Now what happens is, what momentum basically does is, suppose you have point A, you are at point A and you want to go to point B, right? So, and you don't know if you are going in the right direction. So what you're going to do is basically you're going to stop at each place and maybe ask if this is the direction to reach point B, if this is the way, right? Once you start getting confirmations that yes, this is the direction, you will probably increase your speed, right? So this is what happens with SGD with momentum. Once you get confirmations that yes, you are going in the right direction, you start increasing your pace. So let's again consider this similar loss function graph. Say your starting point is here. You calculate the slope, you check that, and then you figure out this is where you're supposed to be headed. Then you stop at another point closer to the previous point, and then you check the slope again, and then you understand yes, you have to go here again. So once you do that, your next stop would probably have a more you can say it will be further apart than what was your previous stop, right? So as you start getting confirmations, the more confirmations you get, the distance between your stops increases, right? So this is how you would reach your global minima faster. So let's understand the mathematics behind this before moving ahead. So say we have to update our weights, right? So what we're going to do is we're going to take our previous weight And instead of having a learning rate multiplied by our gradient of loss, what we're going to do is we're going to subtract it with v at time t. So this is our weight at time t plus 1. This is calculated by subtracting v at time t by w at time t. So what v here is, v at t is basically calculated by beta into v at t minus 1 plus learning rate into weight gradient, right? So what we have here, this part is what is basically our momentum component. Right? Why is this called the momentum component? Well, basically what's happening here is, in order to calculate Vt, we need all our previous velocities. Yeah, so V here is basically velocity. Okay, so in order to calculate Vt minus 1, we need Vt minus 2. To calculate Vt minus 2, we need Vt minus 3, and so on. So basically this is an exponentially weighted moving average, right? Beta over here is going to have a value between 0 and 1. Preferably in general it is 0.9. So this beta over here is called a decaying factor, right? So we can say if beta is equal to 0, this entire thing will turn into normal SGD. How is it so? If beta is 0, this momentum component becomes 0. So all we're going to be left is with learning rate multiplied by the gradient of weight, gradient of loss, right? So this would simply turn out to be normal stochastic gradient descent. So, but if we have our beta which is equal to 1, we're going to fall into a condition, repeat, we will fall into a condition known as dynamic equilibrium, where we wouldn't reach our global minima, rather we would just be traversing fro and back continuously, right? So that is something known as dynamic equilibrium. So that is why our optimum value would be somewhere around 0.9 or 0.5, right? So this is where the momentum component comes in the picture. Let's look at the difference between the graph. Suppose this is our graph, and SGD would look something like this until it reaches the global minima. Say this is the global minima, our starting point is here. So this is how SGD is going to oscillate. But in case of SGD with momentum, our oscillations would reduce in the vertical direction and we would reach our global minima faster. You can see SGD, in case of SGD, our vertical movement is more compared to our horizontal movement. But that is not the case with SGD with momentum, right? So its advantages, it will reach convergence or the global minimum. It will reach the global minima. But the disadvantages, in order to reach the global minima, it will have to do a lot of oscillations. This is not in comparison to SGD. This is in comparison to the better algorithms that we have. So basically, if we have a graph, let's consider the graph above. So as we saw, in case of gradient, we wouldn't be able to reach the global minima in this case, because this has something known as, like, we have to travel in this direction and in this direction at different learning rates, right? But this is possible with SGD with momentum. But the thing is, if we use SGD with momentum, our graph would look something like this. So what SGD with momentum does is it reaches the valley with the global minima, but it will not directly go to the global minima. It will perform some oscillations before reaching the global minima point, right? Before reaching convergence, this is the extra oscillations that it takes. So this is the advantage, this is the disadvantage with SGD with momentum, right? So in order to overcome the issues with SGD with momentum, we have another optimizer known as AdaGrad, or adaptive gradient descent, right? So let's look at the cases where AdaGrad is beneficial. First one is different scales of the data input features. What this means is basically when we have input features like age, salary, number of children, and maybe it's predicting, I don't know, something like maybe if the person is happy or not, right? So these could be our input features where age would range somewhere between 0 to 100 tops. Salary would be 0 to anywhere from billions, trillions, anywhere, right? So there is no maximum limit for salary over here. But number of children, again, it would be 0 to maximum, say 5, right, on an average. So for features like this, AdaGrad would be really helpful. Usually when we have features like this, we perform standardization or normalization. Basically, we scale our features. But in case we have a data set that contains input features like this, we can go ahead with AdaGrad optimizer. The other case is sparse features. Now what sparse features mean is basically, let's say we have a data set of our interview candidates. So let's say we have the name of the candidate. We have a column which says IIT. So we're basically having a criteria whether the candidate has passed out from IIT or not. And then we have our output features selected or not, right? So this could be selected, which is 1, and not selected as 0, right? And this could be the name, and we could have other features like age and CGPA and all that, right? So now, since we know that IIT passed outs are comparatively going to be very less as to the private institutes passed out, right? So we can consider that this feature is going to be sparse. That is, it is going to have more zeros compared to the ones, right? You can see out of 4, we have 1. One data set that has 1 over here. So in case of sparse features, we usually come across a problem which is known as the elongated problem, which we have already seen in the graph above, where we discussed the extra oscillations of our SGD with momentum. So this is basically known as an elongated problem, because as you can see, we in the graph here, something like a valley, like a straight elongated valley forms over here. Now this could have a slope towards this end, but it is mostly straight, right? You can see there's a slope over here, there's a slope over here, but this part doesn't really have a lot of slope. So this forms like an elongated valley, right? So this happens in case of sparse features. We will not go into much detail, but so what AdaGrad does is it allows different learning rates for different parameters, right? So till now our learning rate was same for all our parameters, but AdaGrad, let's see the working for AdaGrad. So basically our weights would be updated like this. The formula remains the same, and so will the bias be updated like this. But the learning rate here and over here. So what our target over here is to have a small update. So whenever we have a big update, whenever our algorithm, whenever our optimizer determines that our update is too big, what it's going to do is it will simply go and reduce our learning rate. So basically whichever parameter, let's call it W1. So in case our W2 is having a really large update, so what our algorithm is going to do is it will go ahead and decrease the learning rate for this specific parameter. So this is what AdaGrad does. Right? Let's see what the mathematics behind this is. So we'll just look at W, similarly B and all our other parameters will get updated. So we're going to subtract the learning rate, again multiplied with our our loss gradient. But over here we divide it, so this is basically dl by dw, right? So but over here we divide it by under root vt plus epsilon. So epsilon is a really small value in case vt is 0. So we do not want to divide anything with 0. So this will reach to infinity and our optimizer will not really work as we expected it to. Right? So vt over here is again our velocity, which we can calculate using vt minus 1 plus delta wt the whole square. Right? So what is happening here is basically it's going to calculate all the past gradients. So, and we square our loss gradient in order to have a positive value. We could have taken mod, but then again in back propagation we differentiate. So that is why we have the square and not the mod of our weight gradient. Right? So this is basically the sum of the square of all our past gradients, as you can see here. So this is how AdaGrad works. Let's look at the disadvantages for AdaGrad. It has low convergence. So as we've already discussed, it decreases the learning rate. As it sees that the updates are getting bigger, it will decrease the learning rate. So what happens here is basically as we move forward, our learning rate keeps decreasing, right? And when it's about to reach the global minima, sometimes the learning rate is so small that moving forward is not an option for algorithm. So most of the times it stops really close to the global minimum and it considers that point as the global minimum. So there is low convergence for AdaGrad. And for this very reason, it cannot be used for complex neural networks. It is a really good algorithm if we're going for something simple like linear regression, right? Which is basically a convex loss problem. But for neural networks, we have graphs which are non-convex. So AdaGrad is not the preferred optimizer in this case. So this is why we have a different optimizer, which is RMSPROP, root mean square propagation. It is the improved AdaGrad, right? So let's look at the mathematics behind RMSPROP. So basically, to update the weights, we use the formula, the old weight, and then we subtract the learning rate multiplied by our loss gradient, and then we divide it by Vt plus epsilon the similar way. But Vt over here is multiplied by beta, which is again going to have a value of around 0.9. We multiply it with our previous gradients, and then we multiply 1 minus beta with our loss gradient, with the square of our loss gradient, right? So since these old values will not get much importance over here compared to our new values, so this is why AdaGrad, this is better than AdaGrad, and it will also reach the convergence. And you will be surprised to know it has 0 disadvantages. So far it is the best optimizer, right? So it doesn't really have any disadvantages so far. So let's look at one example. Let's say we have our V0 equal to 0. So in order to calculate V1, we're going to multiply beta with our V0, which is going to turn out to be 0, right? And then let's say our beta is 0.95. Okay, so 1 minus beta would be 0.5 into our loss gradient square, right? Similarly, we calculate V2, which would be V1. V1 is, so beta is 0.95 into V1, it is 0.5 into loss gradient square, plus we have our 0.05, sorry, this is 0.05, right, into loss gradient square. So this is basically our epoch 1 and this is our epoch 2. So this is how RMSPROP functions, right? Now let's go ahead and look at the last optimizer for this video, which is basically adaptive moment estimation. It is the most powerful optimizer in PyTorch. It is the combination of RMSPROP and SGD momentum, right? It is used in models like ANN, CNN and RNN. So let's look at the mathematics behind this optimizer, right? So we have our weight, our new weight, which is basically calculated by our old weight subtracted by our learning rate multiplied by MT. Let's look at MT, divide by similarly VT plus epsilon, right? So MT over here is nothing but beta 1 multiplied by MT minus 1 plus 1 minus beta multiplied by loss gradient, and VT is the same as our RMSPROP, which is beta 1 VT minus 1 plus 1 minus beta multiplied by gradient of loss square, right? So this MT over here is basically momentum. So in order to have a combination of RMSPROP and SGD momentum, we multiply our learning rate with momentum instead of directly multiplying it with our loss gradient. So this was all about optimizers in PyTorch. Let's go through a quick summary. So the gradient descent optimizers converge, but the problem with gradient descent optimizers is that the speed is very slow. So in order to overcome this shortcoming, we have SGD with momentum. We introduce momentum to overcome the shortcoming of speed. So SGD with momentum reaches the convergence point, which is the global maximum, really quickly. But the issue that arises with SGD with momentum is that it takes unnecessary oscillations before reaching the global minimum, or you can say before converging. So this shortcoming is again overcome by our next optimizer, which is AdaGrad. So now AdaGrad will take the right path, will take the shorter path, will not perform the extra oscillations. But again, there is an issue, that is, it will not converge. It will stop right before or very close to the global minimum. Now, all these shortcomings that we've discussed so far are overcome by our two optimizers, that is RMSPROP and ADAM. So these two are the most powerful, or you can say most widely used optimizers in PyTorch. Using the right optimizer depends on our dataset and our understanding of the model. So this is all about optimizers in PyTorch. If you've liked the video, hit the thumbs up button and subscribe to our YouTube channel. And see you in the next video.